Okay, our next theorem is going to be as follows. Suppose that the function f is uniformly continuous on I, and let's say xn sequence of points in I is a Cauchy sequence. Which means that the sequence converges, but its limit does not really need to lie in I. Then f of xn is also a Cauchy sequence. Let's see what the proof of this fact is. Okay, so how do we show that a sequence is Cauchy, right? We have to select an epsilon greater than 0, right? So choose any epsilon greater than 0. Well, then, because f is uniformly continuous on I, there exists delta greater than 0 such that xn, let's call it, such that x minus y is less than delta, and x and y both belong to I, that this implies that f of x minus f of y, that this should be less than epsilon. Right, so this is true because f is uniformly continuous on I, right? Basically, I just use the definition of a uniform continuity. Okay, so also, I know that the sequence xn is Cauchy. Now, if I would like to make f of x minus f of y less than epsilon, right, I have to keep x minus y to be less than delta, right? Eventually, if I want to prove that my sequence is Cauchy, what I need to do, my sequence f of xn is Cauchy, what I would need to do is to demonstrate that f of xn minus f of xm is going to be less than epsilon as long as n is bigger than, n and m are bigger than a certain number, right? That's a definition of Cauchiness. And I already know that xn is Cauchy, so how can I make f of xn minus f of xm to be less than epsilon? I just need to make sure that xn minus xm is less than delta, right? And because xn is Cauchy, I should be able to do this. So xn is Cauchy, and therefore there exists a capital K in R, or we typically use capital N, so let's use that. There exists a capital N in R, such that if n and m are both greater than capital N, then xn minus xm is less than delta, right? The same delta that I found in here, right? Okay, but in that case, if xn minus xm is less than delta, because for any 2 points in I, if x minus y is less than delta, then f of x minus f of y is less than epsilon. So then from that it follows that f of xn minus f of xm is going to be less than epsilon. So in other words, for any epsilon greater than 0, there exists a capital N and R such that n bigger than n and m are bigger than capital N, that this implies that this is true. So that means that the sequence f of xn is Cauchy. So this is true as long as n and m are bigger than capital N. So, like I said, f of xn is Cauchy. And so the proof is completed. How can we use this to in our examples, this theorem in our examples? So basically the theorem says that if I have a Cauchy sequence on x-axis and I apply a uniformly continuous function to it, then a sequence of values is also uniformly continuous. So let's go back to one of our examples. And I believe that was example 3, if I am right. Example 3, yep. Let's do this. Let's consider any sequence on x-axis that converges to 0. For example, let's make xn equal to 1 over n. Then the limit as n goes to infinity of 1 over n is equal to 0, right? And therefore, xn is a convergent sequence, and any convergent sequence of real numbers is a Cauchy sequence. In fact, any convergent sequence is a Cauchy sequence. So therefore, xn is Cauchy, right? Okay, now let's suppose that f of x equal to 1 over x is uniformly continuous on the interval from 0 to 1. We know that this is not true, right? Because we already showed that in this case, common delta in epsilon delta definition of continuity does not exist. So let's see if we can apply the theorem that we just proved to show the same fact. So if we consider f of x on the interval from 0 to 1, and we assume that f is uniformly continuous, then what do we have? We observe first that the sequence xn of 1 over n's, it lies inside I, right? Or because I did not introduce I, we just say It lies inside the interval from 0 to 1. Okay, so then from the theory that we just proved, xn is a Cauchy sequence, right? And if f is uniformly continuous on the interval from 0 to 1, then f of xn is a Cauchy sequence. Right? Okay, so if I have a sequence if I have a Cauchy sequence of real numbers, I know that that sequence must converge in a set of real numbers, right? So therefore, f of xn converges to a real number. But on the other hand, what is f of xn? In this case, I know exactly what f is, and I know what xn is, right? Xn is 1 over n, and f is 1 over x. So it's 1 over xn, which is 1 over n equal to n. And what happens to n when n goes to infinity? Of course, this goes to infinity. So on one hand, we have that f of xn has to go to a real number, and on the other hand, f of xn has to go to infinity, and that is a contradiction. And so from this, we can conclude, so therefore f is not uniformly continuous on 0, 1. Right, so by using this theorem, I can avoid playing with epsilon delta definitions again. So let's do an intermediate summary of what we just were talking about. We proved a theorem which said that if a function is continuous on a closed bounded interval, it must be uniformly continuous. So then if I have a function on a closed and bounded interval, which is continuous, I know immediately that it is uniformly continuous. On the other hand, if I have a function on an interval that may be bounded but not closed, or possibly interval that is not bounded, then I cannot apply this theorem anymore. It is still possible that the function is say continuous on a closed and unbounded interval, and it's still uniformly continuous. I'll give you an example towards the end of this lecture. So in particular, I cannot actually prove that the function is not uniformly continuous by using this theorem, because the theorem is not if and only if statement. Continuous on a closed bounded interval means uniformly continuous, but uniformly continuous does not mean that the function should be continuous on a closed and bounded interval. We already actually saw an example here, right, that if I have a function square root of x on an open interval from 0 to 1, right, this function is uniformly continuous, but it's not defined on a closed and bounded interval. So then to disprove that the function is uniformly continuous, I have to do something else. And one of the tools is a theorem that I just proved, right? That if the function is uniformly continuous, it has to map Cauchy sequences to Cauchy sequences. So if I want to disprove that the function is uniformly continuous, just like here, I can provide an example of a sequence which is Cauchy on x-axis, but once I map it to y-axis, it's no longer a Cauchy sequence. Maybe let's do one more example. So let's go back. So now return to example. Let me see what it was. To the example with oscillating function right here. So example number 4, we had f of x equal to sine of 1 over x on the interval from 0 to pi over 2. And we saw because this function oscillates infinitely fast between -1 and 1, as x goes to 0, it's not uniformly continuous. So let's try to use the same Cauchy sequence argument here to prove this. So to example 4, sorry. So I'm going to try to do the same thing. What I need to do is I need to find a convergent sequence on x-axis which converges to 0, such that along the sequence, sine of 1 over x is not going to give you a convergent or a Cauchy sequence. How can we do that? Basically, I'll try to pick off the values of sine at, so sine oscillates between -1 and 1. And I want to select my sequence xn in such a way that it will go through these values plus and -1. And if a sequence oscillates between plus and -1, then it's not going to converge. So let's see. Sine is going to be plus and -1. So let's say want to show that f is not uniformly continuous on the interval from 0 to pi over 2. So what do I know? I know that sine of pi over 2 plus pi n is equal to what? So if n is equal to 0, right, we have just pi over 2, sine of pi over 2 is 1. If n is equal to 1, we have sine of 3 pi over 2, that's -1. And so this sequence is going to oscillate between plus and -1, so this should be, if you think about it, -1 to the power n, because if n is 0, -1 to the 0 is 1, if n is 1, -1 to 1 is -1, and so on. So because this is true, I'm now going to, so let me move things around again. So because this is true, I'm going to set xn to be 1 over pi over 2 plus pi n. If I do so, then of course the limit as n goes to infinity of xn, right, top stays equal to 1, denominator gets bigger and bigger, so this limit is 0. So xn is a convergent sequence, and therefore xn is a Cauchy sequence. Right? So now let's suppose that f, our sine of 1 over x, is uniformly continuous on the interval from 0 to pi over 2, right? Certainly it is continuous on this interval, right? Because if x is not equal to 0, then sine of 1 over x is going to be a continuous function. Okay, so then by the theorem that we proved last, f of xn is Cauchy, and therefore sequence f of xn, f of xn converges to a real number. Right? On the other hand, what is exactly f of xn? F of xn is sine of 1 over xn, which in our case is going to be sine of 1 divided by what's xn? 1 over pi over 2 plus pi n, which is sine of pi over 2 plus pi n, which in turn is minus 1 to the n, as we already seen here. Well, and so then the sequence f of xn, right, minus 1 to the n is not a convergent sequence. Does not converge. But according to our assumption, it does converge to a real number, so that's a contradiction. And so we're done, right? We proved that the function is not uniformly continuous.